Hello, I'm Jim Levis and I'm a Research Assistant Professor at North Carolina State University. In this presentation I'm going to talk about an introduction to lifecycle assessment modeling with specific focus on solid waste management applications. We should begin by defining what is lifecycle assessment. Lifecycle assessment, or LCA, is an objective framework for evaluating or assessing the environmental impacts associated with a product, process, service, material, or system across its entire lifespan from cradle to grave. So when we look at this figure here, which was produced by the EPA about 8 years ago, we look at the gray box and we look at a typical product that includes raw material acquisition or manufacturing. If you think about something like a car, it's going to take a lot of steel, which is going to have to come from iron ore, which is then going to need to process into steel. And then we're going to take all of our components, we're going to manufacture a car, and there's emissions and energy use associated with all of that. Then you're going to drive around in your car, you're going to produce more emissions while you're driving around, and then finally it'll be time to scrap your car, and a lot of that steel is going to be recovered and it's going to be recycled into new cars. Things like your tires could be combusted for energy, or they could be turned into asphalt, or they could be chipped up and become playground material, and then some of it, or and a large portion of it, is also going to end up in a landfill. And so all of those, each of those stages has inputs and outputs associated with it that we need to consider in a life cycle assessment to fully understand the life cycle environmental impacts associated with that product, process, or system. So how can lifecycle assessment be applied? We can use it to evaluate alternate solid waste management strategies or improve our process or system. It can guide product design or product use. And we can also use it to present sound quantitative technical information to policymakers in a format that should be easily understood. And the general hope is that we can use this framework to bring science and policy together more, and to kind of cut through a lot of the environmental fog and claims that are made and provide some real quantitative background and analysis. So typically, life cycle assessment is defined as having 4 stages. There's goal and scope definition, which is sometimes broken into goal definition and scope definition. There's also the inventory analysis stage, that after we've defined the scope of our study and what we're doing, we actually then need to quantify what are the emissions and impact, or what are the emissions and outputs and inputs associated with all the processes in our system. And then we take our inventory results, where we have all of this huge list of emissions associated with our product, process, or system, and we try to actually turn that into and determine what are the environmental impacts associated with those emissions. So if we have a list of 100 emissions, what's the actual harm to the environment from that? And then finally, we have the interpretation and improvement stage, where we take all this quantitative analysis we've done and we look at it and we try to figure out what do the results tell us, how could we build a better analysis, what data is needed to build a better analysis, and is everything consistent across our stages. In the inventory and impact assessment, was that done consistent with our goal and scope? Did we answer the question we set out to answer? And we look at all that in the interpretation phase, and when you look at all these arrows, you see that each stage is informing the other stages. And that brings us to the fact that assessment is an iterative exercise. It's not just one and done. You walk through the 4 stages and then you walk away and you quit. It's meant to be iterative. It needs to be iterative. You need to walk through it, starting with your goal and scope and defining a goal and scope that makes sense through your inventory analysis, through your impact assessment. Interpret your results, look at how you can improve your analysis, make sure your initial goal and scope are actually answering the question you meant to answer. You can adjust your scope, narrow it, broaden it to make sure you're really getting at the question you need to answer. And then you can go back through and get more results and reinterpret. And the idea is just to keep moving till you really hone in and converge on the solution to the question you really needed to ask. So a good way to look at those different stages of life cycle assessment is, what are the questions we're asking in each stage? So in our goal definition, we're trying to figure out what's the purpose, what's our target group, basically, why are we doing this, what are we doing this for, and what are the decisions we're trying to support. And then, so once we know why we're doing this and what we're actually trying to analyze and what decision we're supporting, we need to look at what are the actual products we want to consider. So if you wanted to, in your goal, look at solid waste management, whenever you try to determine solutions, whether you consider just current technologies, landfills, MRFs, waste to energy, do you want to look at future technologies, plasma arc gasification, or do you want to look at things people don't really use that often, or mixed waste composting or something like that? So in the scope, you need to actually take your analysis and figure out, okay, what am I really looking at? What's the scope of what I'm going to model? Looking at what environmental exchanges I want to consider, what really matters, and how am I going to answer the questions raised in my goal definition. Then we do the inventory, and we need to figure out, okay, how good, what are my data requirements, how certain does that need to be, how are we going to actually model the system, what data do we need, what processes are we including, how are we going to get that data. And then in the impact assessment, we need to answer some similar questions of, well, how are we going to take those inventory results and turn them into actual environmental impacts? What contributions to the environmental harm are most important? What sources of emissions are most important? And what are the uncertainties or knowledge gaps that are most important that we may want to actually consider when we look at the next stage or the next iteration or in the interpretation phase? So when we define our goal and scope, we're figuring out what is the purpose of the LCA, why are we conducting it, who's going to use these results, how are they going to be used, and how broadly do we need to consider alternatives. Once again, are we considering current technologies, future technologies, far future technologies, rocket ships that take our garbage to the sun, or some subset probably, something in between, and what are the issues or concerns that this study will actually address. So when we're defining our scope, the whole idea is the first thing we need to define is our functional unit, which is the objective of our study. And we'll talk a little bit more about functional units in a couple slides. But we could look at 1 ton of MSW generated, a ton of recyclables at a MRF, or any other potential functional units. We need to define the boundaries of our system and the exchanges or emissions we're actually going to consider as they cross those boundaries, as well as the assessment criteria to be applied, whether it's global warming or eutrophication or fossil energy use. And then in our scope definition, we need to also look at the time scale of our study. So waste composition could change, landfill emissions are delayed, we could store carbon in soil or landfills. Once again, figuring out what are the actual technologies we're looking at, as well as allocation processes, which is an interesting concept we'll get into a little more later. But looking at what are the actual benefits of recycling glass? What are we avoiding? If you recycle glass as actual another glass bottle, that would be different than if you take your glass and you recycle it as mixed glass aggregate, let's say, or that you use to build glass fault roads or something. And then if you produce electricity, what are you actually avoiding? What are the real benefits associated with that, generating that electricity? So once again, I said that idea of function and functional unit is essential to life cycle assessment. So the function is the service that's actually provided by your system. So it could be solid waste treatment, electricity generation, fuel production, and then our functional unit quantifies that service. So we could look at a ton of MSW generated at curbside, a ton of MSW received at a facility, a landfill or waste to energy. We could look at a megawatt hour of electricity generated from landfill gas to energy versus waste to energy. Compare that to conventional electricity sources like coal or natural gas. We could look at meter cubed of CNG production from landfill gas or from anaerobic digestion, and we could then compare that to other ways to produce CNG, conventional CNG production. So defining this functional unit is essential for figuring out, essentially for doing the right analysis to answer the questions we want to answer. So all of that also, once we've defined our functional unit, we really need to define our system boundaries, including all that is relevant and only what's relevant. You can look at, your system can essentially expand to include the entire global economy if you let it. So somewhere along the way, we need to cut off our system boundaries to model only the things that are really relevant to the question being answered in our goal definition. So there's different ways to think about system boundaries, And the traditional life cycle assessment can be cradle to grave. You can also have systems that are cradle to cradle if you have a material that can be 100% recycled back into the same product. And that goes all the way from raw material extraction to end of life management, similar to the diagram I showed on the second slide. You can also do a cradle to gate analysis where you're looking at, okay, raw material extraction until, let's say, your company produces a product. And a cradle to gate could be very useful if you're looking at different material sources for your product, or maybe different processing choices, but you're still ending up with the same product. So all of the use phase and all of that is kind of irrelevant to the decision you're making. And then you can also look at a gate-to-gate facility where you're assuming all of the inputs to your process are still the same and the outputs are the same. And really this would be for optimizing or making decisions within your facility that won't affect your actual raw materials coming in or the product coming out, so all of that's irrelevant. But then you can really just focus in on what's going on in your processes to use those inputs to make those outputs. And then, so when we define our system boundaries, we also have this concept of system expansion or substitution that is essential for solid waste processes. If you look at the non-comparable systems on the left, we have a waste facility that produces some residual as well as 1,000 kilowatt hours of electricity. And we can't compare that directly to a facility that just takes waste and then residuals. We need to expand our system boundaries because there's that added benefit of we made 1,000 kilowatt hours of electricity, we should get some sort of benefit associated with that. And so typically what's done is the process on the bottom right where we use a subtraction, and basically what we do is we take our waste facility that produced the electricity and then we subtract the emissions associated with generating that would have been produced while generating that electricity. So that could be 1,000 kilowatt hours of coal electricity or average electricity or natural gas, and there's a lot of decisions that need to be made with that, and that goes back into our allocation criteria that we defined also in our scope definition. And now we can compare those two systems. You can also do this with addition in the upper right alternative. That's much less common because now what happens in the left system is affecting what you're modeling in the right system, and it's a lot harder to model that because now your two scenarios are directly linked to each other, and it's much easier to do the subtraction where each scenario is still independent of each other, but we're still modeling and comparing comparable systems. So once again, to get back into to discuss the temporal issues related to system boundaries, lifecycle assessment traditionally doesn't differentiate between impacts by time. They either happen within their time horizon and they count the same, or they happen outside of your time horizon and they don't count at all. For solid waste management, this can be interesting because something like a landfill can have environmental impacts well beyond 100 years. They can be still producing gas, still producing leachate, and so there may be ways to actually think about how to include those emissions in our life cycle assessment. If we sequester the carbon, or there could be stored toxicity of leachate that hasn't harmed the environment, but it could harm the environment after our time horizon. And also with life cycle assessment of solid waste systems, we need to remember that we're building long-term infrastructure. So we need to consider how our system is changing with time, whether it's population, waste generation, or composition, as well as policy changes to the energy system. That if we're looking at a facility meant to last 30 years, we need to consider how it's still going to respond 30 years from now. So this is an example for collection activities where we start with our collection vehicle and the garage, and we're doing a life cycle assessment of those. And then those both cost money. And we have emissions associated electricity use and natural resource consumption and emissions associated with our trucks and their fuel, as well as the garage. Also, to run our trucks, we need petroleum, and there's emissions associated with generating petroleum, extracting crude oil and then refining it and transporting it. And then also to get the electric power, we need to generate that. We need to transmit it there. to where we're going to use it. We're going to manufacture a truck, and that's going to produce emissions and electricity and natural resources as well. And then you could come up with any number of other things that we're still using to make the garage, manufacturing the garage, let's say, or the equipment to manufacture the garage. This just tells us that coming up with appropriate system boundaries is essential for actually being able to perform your analysis and include everything that's relevant and only the things that are relevant in your analysis. So in our scope definition, we also need to define our assessment criteria, and they need to be consistent with our goal and scope definition. So we could look at global impacts like global warming or ozone depletion, regional impacts like smog formation, acidification, eutrophication, toxicity, or even local impacts like land use or odor or stored toxicity, spoiled groundwater. And all of these are emissions-associated impacts. We could also look at resource depletion that could be at any one of these scales as well, like oil, coal, aluminum, fresh water, phosphorus. And so in our scope definition, we also need to consider all of these things, basically decide how we're going to decide which alternative is better. In our inventory analysis, or also called life cycle inventory, is our next stage after our goal and scope definition. And in this stage, we're going to be describing all of the inputs and outputs in the product's life cycle from cradle to grave. Basically, all of the process that we included in our system boundaries, we need to know the energy and material flows in and out of those products. It's similar to what's done in a framework called material flow analysis, or MFA. An MFA can kind of be part of your inventory analysis, or it's often just a standalone analysis procedure as well. So, and then the whole point of the inventory is we want to quantify all those inputs and outputs and emissions. And then so in defining our inventory analysis, we need to itemize all those inputs for every single process within our system boundaries. And once again, lifecycle assessment is meant to be iterative. So you could do part of your analysis, realize you need to expand your system boundaries or narrow your system boundaries depending on if something really doesn't produce an impact that matters that much. You could realize, oh, this should actually be outside my system boundaries, or your preliminary results could say, oh no, this really is important, and now we should add it to our system boundary. A key part, if you're trying to actually model all of the inputs and outputs and material flows through every process in your system, data is essential. And there's multiple data sources available. You could look at peer-reviewed literature or books. There's not a lot of, you can have difficulty finding direct inventory results in the peer-reviewed literature, but some is definitely available, depending on what you're looking for. You could extrapolate from similar processes. There are databases of lifecycle inventory results from EcoInvent is probably the largest, and it's commercial database. And then there's NREL, which is also called the US LCI database, which is free. The popular lifecycle assessment models, SEMAPRO and GABI, also have their own databases. You can also gather data through questionnaires of operators and their fuel use or their electricity use. So you could do surveys and things. You can also do models based on how much you know about the process. You can try to estimate fuel, material use, or electricity use. You can take your direct measurements or look at average performance over an entire industry, let's say. So this shows a conceptual mass balance for a waste system. We have waste and fuel and water and other materials coming into the system on the left, and coming out we have emissions to the atmosphere, emissions to the soil and water and wastewater. We also have some remanufacturing or recycling. Some of our material leaves the system to go become new materials, or we can produce soil amendments and composting or digestate to be used on the land. And it's also not shown, but we can also store waste, obviously, in, say, a landfill. So an example of math balance with some actual numbers. So this is a pretty simple system that includes composting, landfill, and a paper MRF. We're generating 35,000 tons per year of waste, and then it's split between the three facilities, and then it ends up being emitted to the air, or it comes out as compost or paper or paperboard from the MRF. The landfill generates emissions as well, and the landfill also stores a lot of the mass, not quite 50% of it, that doesn't actually leave. But all of the arrows in and the arrows out in your stocks need to obviously balance. That's the mass balance. So whenever we're doing the mass balance, the general idea, like all mass balances, track all the weight, all the mass in and out, don't forget anything, as well as all the emissions and the energy being consumed and used in each process, and tracking that all the way back throughout your entire system boundaries. This brings us to the idea of pre-combustion emissions. Basically, the idea of pre-combustion emissions are emissions for fuels that happen before you combust it. So basically, you combust it, but before you actually get the fuel in your car, you had to refine crude oil. You had to extract and refine crude oil and then distribute it. And so this analysis is for I think it's for diesel use in Europe, and 15% of emissions are associated with actually getting the fuel to your vehicle, which is not the majority, but it's certainly significant, and you need to remember to include that as well in your boundary. So this is building on the previous one that showed the mass balance, is an actual analysis of all the emissions associated with each of these processes, from CO2 and ammonia, or all the CO2 and ammonia emissions from each of these, collection and transport, in the paper MRF, mostly electricity used with that, associated with that, transport emission, composting emissions, landfilling emissions as well, and then there could be savings associated with recycled paper and cardboard. You'll see circled, there's a negative CO2 fossil from the landfill, and the meaning of that negative emission is, you actually saved CO2 fossil emissions if we assume our landfill made electricity, and that avoided electricity would have come from coal, let's say. And so you can end up with negative emissions that say we actually saved some CO2 emissions by doing this other beneficial thing. That brings us to the whole idea of recycling and beneficial use. When recyclables are converted to new products, we essentially we use resources and produce emissions in actually turning that recyclable into the new product. But there's also savings associated with extracting, processing, transporting virgin materials to produce that same product. We also look at so instead of products, you could also look at generating electricity from either combustion or landfill gas or anaerobic digestion, and then you end up with that electricity offset, that there's some electricity that wasn't generated somewhere. Composting and anaerobic digestion can produce digestate or compost, and then there can be benefits associated with that. They could, depending on if they have the nutrient content of them, or they could offset peat use. And so considering that whole expanded system boundaries to look at what is being avoided when we produce these beneficial products. So whenever we're doing material recycling, we basically calculate our net emissions. They're the emissions we actually it's the difference of the emissions from processing the recovered materials. So actually, if it's paper, repulping the paper and all that, minus the emissions avoided from virgin production. And then there could be also a substitution factor in there that, say, your recycled paper can actually only be 60% recycled because the fibers keep shrinking as it's recycled more and more. And this gets interesting because in the first note, if all this happens at the same plant, it's really easy. There's this obvious link between the virgin production and the reprocessing, so calculating this is relatively easy. But if they're happening at separate plants, then that direct link can't be made, and now we're starting to make links based on the overall market. And as you can think, if you just think, there's a lot of issues that could be associated with that. And the actual benefits could be more difficult to estimate, and you'll need to think harder about your allocation criteria. So at the end of our inventory analysis, for our two alternatives, whether it's landfill or waste to energy, that we could be comparing, we'll end up with a long list of emissions and substances to the air, to the water, and we need to somehow use all of this data to meet the goal of our LCA and try to answer which one of these alternatives is better or preferable. So we start out with an inventory like this that just shows a great deal, a number of emissions to the environment, and the whole point of impact assessment is to try to make sense of that long list of emissions or exchanges to the environment so we can actually aid interpretation and determine which one of these is preferable. And we do that by, we can take those results and we can develop, use impact factors to determine what the actual impact on global warming or ozone depletion or acidification is, and then we can take optional steps like normalization and weighting to try to further make the results easier to interpret, all the way some people do to one final score that you could call environmental harm score or some environmental indicator that you can say, oh, B is 37 and A is 12, therefore B is better. And this whole process, I just want to be clear, is there's trade-offs associated with it. Our life cycle assessment, each of those numbers, there's still uncertainty associated with them, but we've run good models, they're built on good data, and those are fairly certain numbers, or at least we can use, sensitivity or uncertainty analysis techniques and understand quantitatively the uncertainty in those ranges. The problem with that inventory is it's very hard for humans to make decisions based off of 120 different variables. So the whole point of the inventory, so we can take those results, get some impact results, which is in the upper right, and now we have fewer categories and we actually have some understanding of the environmental harm and we can compare things more, but we lost some uncertainty. That blue arrow to the right, we don't actually know, we've just added more uncertainty to the model. And then if we do normalization and weighting, it once again makes interpretation easier because it's easier to compare fewer numbers, but you've added more uncertainty to the models. So that trade-off is always there between model uncertainty and interpretation difficulty. So the entire purpose of impact assessment is taking the inventory results and trying to help us interpret them and make rational decisions. So we need to actually quantify how those different environmental emissions or exchanges affect the environment or impact the environment. And then also, is there some way we can also look at, is there some way to rank environmental harm, like global warming potential versus toxicity? And some people have thought about that as well. And this whole phase of the life cycle assessment is called the life cycle impact assessment. So life cycle impact assessment, it aggregates the life cycle inventory data to support interpretation. The choices of how we do this aggregation need to be consistent with the goal and scope definition. So there are things we call areas of protection, like human health or the natural environment or natural resources. And those are things, when we're doing an assessment, that we very broadly want to protect. And we can do that by looking at different kind of midpoint indicators, like human toxicity or radiation or carcinogens or climate change or ozone layer depletion or smog. And then to get those and to estimate the impacts on those midpoints, we need to use our inventory results and some other additional models to put all of those emissions, associate them with different midpoint indicators of environmental harm. So the 4 stages of impact assessment are classification. That's that going back and assigning each emission to the impacted categories that it affects. Characterizing the emissions. So if we know methane causes global warming, well, how much global warming does a kilogram of methane cause? So that's how much does it contribute. And then we can normalize it and say, is that a lot? So if I have 100 tons of, if I emit 10 kilograms of methane, is that a lot of methane? Is it not a lot of methane? Can we just do something, and the whole point of normalization is to try to just do some relative comparisons to just say, well, how much is that compared to something I can actually wrap my head around? And then the purpose of weighting is to actually say, okay, but if I look at the overall normalized results, and I could say, do some sort of modeling to look at, okay, I have this much global warming and this much acidification, then which one is actually harming the environment more? And there's some techniques for doing that. And kind of as I discussed before with that addition of uncertainty, normalization and weighting steps are actually both considered to be optional in life cycle assessment, and that's because for your system and for your analysis based on your goal and scope definition, that trade-off may not be worth it. Basically, making the interpretation easier may not be worth it, the uncertainty you're adding in the normalization and weighting steps. So that's why they're optional. So typical LCA categories, we've kind of mentioned these: global warming or acidification, eutrophication, toxicity, land, water, resource use. This is an example of how we actually do the characterization step of life cycle assessment. So this is the general equation. Our life cycle impact equals the sum of the product of our characterization factor for our pollutant P. So we have a characterization factor for each pollutant, for each impact. For most things, it's going to be 0. And we multiply that by the actual mass emitted of pollutant P. And so when we sum over all the pollutants, then we get our total impact. So for global warming potential, you may have heard of the term global warming potential. So the global warming potential is the characterization factor for global warming, and it's measured in terms of kilograms CO2 equivalents, usually based on 100-year radiative forcing. So for methane, it's 25. So methane traps in 25 times the heat of carbon dioxide over 25 times more heat than carbon dioxide over 100 years. So a further example for global warming impact, so for CO2, since it's our baseline, it's just 1 for stored carbon dioxide. So if we store carbon dioxide in a landfill, that's -1 because we took fossil emissions out of the atmosphere. For methane, it's 25, and for N2O, it's 298. And then you can get for things like different CFCs or HCFCs, they can be in the thousands or even 10,000s. So the whole point of the interpretation and improvement is to consider the goal, scope, and the results of the inventory and impact analysis together, and to look at how they could be improved and what should we do in the next iteration. Where can we improve data? Should we expand or limit our scope? Did we actually answer the questions we set out to answer when we started this? Or do we need to do more analysis? What is the decision we should make based on this entire analysis? Can we make that decision, or do we need to do more analysis? So there are limitations associated with life cycle assessment. Life cycle assessment may be more difficult when things are really site-specific. For example, NOx emissions could be much more important in some areas of the U.S. than others. Water consumption, fresh water consumption is an obvious example where the site-specific issue comes into play. Using excess fresh water in North Carolina is very different than California right now. And so keeping track of local versus global emissions or regional emissions can be difficult. Like I mentioned before, keeping track of the temporal issues can also be difficult. I would like to acknowledge the National Science Foundation and the Environmental Research and Education Foundation for their support of this research. Thank you very much for your time.